Cool, let's work on another problem. Today we're going to be working on number 108, convert sorted array to binary search tree. So, given an integer array nums where the elements are sorted in ascending order, convert it to a height-balanced binary tree. A height-balanced binary tree is a binary tree in which the depth of the two subtrees of every node never differs by more than 1. Okay. So we're given an array something like -10, -3, 0, 9, 5, and then 9. Okay. Let's see. If we just went left to right, so let's say left to right, since the number will always be bigger in terms of BST, so we start at -10, so we can say if no root exists, that create the new node and have that as the root. So let's say -10, there's no root yet, so we create that, and then we set that as a root. -3. -3 is larger, so we move that up. Now the interesting thing happens at 0. We have two choices essentially. We can either put 0 here as a right node of -3. So at the third item, we can either place it as the root.right or as the new root. What drives this choice? What happens when we add it to the right? So now we have -10, -3, 0. Then when 5 comes along, 5 comes up here. Would that be a valid binary tree? I'm honestly not sure. It's been a while since I've done a binary tree. Let's see. If we were to have it here, if we had 0 here and 5 here, it would go here and here. I would assume that that's valid. And then 9 goes on the right. I think the problem that happens at that point is that if we were to add more, then we would start getting sort of like a biased binary search tree, if to a certain extent. At the same time, we could always do another strategy where we say start with the root, which will always be in a balanced BST in the middle of the array. So we start by taking this array, grab the middle, and make that the root. Then we just use our standard binary search tree insertion algorithm. Sorry, I can't type today apparently. So we start at 0, then we start at the left side, so -10, then we do -10, -3, then 5, and then 9. And that seems to produce this on the bottom, which makes sense. And if nums is sorted in a strictly increasing order, does that mean that there are no duplicates? Because in that case, then I think this would be fine. How long would this take? Well, creation of the root. And the reason why I say this should be fine is because if duplicates were allowed, we would need some other way besides value checking to skip the middle. And that could be like, oh, if the index that we're at is the middle, and we can just skip it. That's also another way to do it. And in that case, we wouldn't need to worry about duplicates. Though we would still have to worry about duplicates in the context of this binary search tree. So creation of the root, I'm assuming that it's constant time to find the middle of an array, because you just take the index of the length divided by 2. I'm assuming that the length is something that doesn't take a lot of time. It's not like a linked list sort of thing. Then going through each node and adding it, this would take O of log n for each insertion, because the height of the tree, log base 2 of n. N times, well, technically n minus 1, but you get the point. So the total time here is probably O of n times O of log n. So that's O of n log n, which, now the question that I'm thinking is that fine? I think given the context that I have right now, that's the most straightforward solution that I can think of. And I'm just currently thinking in my head sort of, is there a better way of doing this? Is there a faster way asymptotically of doing this? And I think the question to that is no. At least my immediate thoughts. We are going to need at least to scan each item within our number array. So we can't really go under O of n because we have to add all of them to some sort of data structure, in our case the binary search tree. And in this case we need to apply this operation to each of them. And unless there's a way to determine where it should belong within the context of a binary search tree in constant time, I don't believe that we can do faster than O of n log n. Now, I could be very much wrong, and again, trees and graphs are surprisingly one of my weak spots and something that I really need to put more focus into. However, this is where it's at right now in terms of what I think, and I think this is where I would start coding it up. So, let's get started. So we're going to start by saying, do we have at least one value? Yes, within our constraints, we have that there is at least one element in our array. So we can say val root is equal to tree node with a constructor of nums length divided by 2. And then we can say nums for each number if number is not root dot val. So if it's not, because this is strictly increasing order. So in that case, I assume, unless my math terminology recall is incorrect, strictly increasing means that we have no duplicates. All numbers must be increasing from the previous value. So we're safe to use this assumption. So if it's not, then we can say, let's see. We'll create a node value which will be of type tree node nullable, and we'll initialize that at root. And let's see. While the node is not null, if the node value, or if our current value is less than our node value, so if our current number, or if the number that we have is less than the number here, then we should say node is equal to node.left. We know that the root will be existing var target. I know. If node dot left is equal to null, node dot left is equal to tree node num. And node is equal to node dot left. Let's start by creating this node. So val new node, which is a tree. Actually, we don't need to declare this because it should be implied. Tree node of value num. This is basically our runner. And let's see. The question now is just how do we insert it and how do we insert it and then break out? I'm just thinking about that. Let's see. Because this won't actually do it. Because if left is null, and then we need to insert a break statement here, which I'm not too happy with. If node.right is equal to null, node.right is equal to new node, break, node is equal to node.right. And this needs to be nullable, otherwise this will never return. Actually, this would never return regardless, if we don't find a spot for it, which we should always find a spot for it, but this could honestly just be a while true. But this is the software engineer in me says this is not good at all. So let me take a little bit to actually go ahead and think about this some more in terms of how I want to implement this. But in the meantime, let me just do a return root at the bottom, because we're going to be returning that no matter what. But how do we do this in a way that we don't make ourselves look absolutely stupid? I mean, we could use a debounce, or not a debounce, but a flag basically saying whether or not we've placed it. That's one way. Because there's not really a lot of many good ways that I imagine I can do this. We could actually break this out and then just return it. That's also one way to do it. Right, that would effectively be this, but without the break. But would that actually change anything? I mean, we could sort of do a recursive sort of input, a recursive sort of place. But I think this is a little bit more effort than I really is necessary for the scope of this problem. I think this is a little bit of an ugly solution, but I think it gets the job done. In an actual engineering situation, I would probably factor this out into its own method to place it. The cleanest solution would be to use a recursive solution, and we call the function we recurse on the left or the right, as long as it is non-null, the left or the right. If the left or the right where we want to go is null, then we place it there, and then we return from there. We place the new node, we return from there, and everyone goes home happy. And you know what? It might be a little bit slower, but I think it's just a nice practice regardless. So let's say add to BST with a root which is of type tree node. And we can say if num, which is int. So if root.val, or let's just keep the logic the same, right? So put num first, less than root.val. If root.left is null, else add to BST root.left num. Else, if root.right is null, to BST root.right num. And we can say root.left is equal to tree node of num, and then return from there. And root.right is tree node num, and return from there. We can say add to BST we want to add it in from our root, our number. So yeah, so this effectively does the same thing except in a recursive manner. So we've removed the infinite loop in favor of a more recursive solution, which does add a little bit of overhead, but it looks syntactically a little bit nicer, I suppose. So if the number is less than the current node that we're at, then we go to the left. If the left happens to be null, then we just create that new tree node and attach it there. Otherwise, we'll just recurse on the left side. And a similar thing on the right side. So if it's not less, we assume that there is no equal. So it'll go to the right. If the right is null, we create the new node. Otherwise, we recurse on the right side. Same thing as before. O of log n sort of traversal type beat. And yeah, so this is pretty much our solution. Sort of, I guess, like 6 lines in the main, and then like another like maybe dozen or so lines to add to a BST. Let's go ahead and run our code to see if there's anything iffy about this that we need to redo. Seems like I've already forgotten. Collections have size, strings are length. Okay, so it seems like it worked for this solution. Let's go ahead and run it on the other solution with the input array of 1 and 3. Seems like that ran fine. Let's go ahead and run a submit and see if there is really a better solution that we should have thought of in the meantime as we were implementing this. Oh, interesting. We got a wrong answer. 0, 1, 2, 3, 4, 5. And what did we end up getting there? We got 304 null, 1 null, 5 null, 2. Wish there was a way for me to sort of visualize this. Because I don't think this... Yeah, I don't think this particular problem has that tree visualizer thing, which is unfortunate. Let's see what's happening here. So when we take 3 as a root, we get 0, 4. We get 0, 4 as our... because 0, 1, and 2 all go on the left side of our tree. So it'll go 0 as the left leaf, then 1 on the right side, and then 2 I see on the right side again. Interesting. So I guess it really isn't as simple as I imagined with this. So looking at this, yes, if we have too many monotonically increasing at the same time, we sort of need to find that middle ground to connect in order to create a balanced tree. So ideally, I'd like sort of to get this 1 here, and then this 5. But this 1 is way more important. I need this 1 to be here, so then it can support those 2. And I initially had a different sort of approach that I was thinking about of whether or not I wanted to go with a sliding window of size 3. And the idea is that we start with sliding windows of size 3, and we sort of just collect all of these little trios and connect them together. However, I'm not sure if that'll actually work the way that I expect it to. And that's the problem. Let's see. If we did that, how much would we have to change up our solution? Well, we would have to sacrifice a little bit of space in order to store more references. Basically create a list of root nodes that then we would combine together. I think having this root node in the middle having this sort of base root node does still make sense. I'm just not entirely sure how to go from there. I'll have to give this one a little bit more time to think about. I'll come back when I either give up or think of possibly a solution. Okay, again, this tablet has been very, very useful. And I recommend anyone who is actually currently studying in college, really for any reason, honestly, to get one of these tablets. I prefer it because it just stores everything. I don't need to haul around a bunch of notebooks or things like that. Though I do appreciate the tactility of physical medium. Anyways, back to the problem. One thing I was thinking is that the problem is that in the solution of this 0, 1, 2, 3, 4, 5, the 0 is the left side, this is the middle, and this is a right side. This is a root. This is the left side, and this is the middle. So I think in this case, there might be a way for me to sort of fake a pattern, or not fake a pattern, but take this pattern of left, middle, right, and extrapolate this to the next level in the sense that let me try to collect my thoughts. This left, middle, right constitutes one trio that is complete. And this, or perfect, one perfect trio. If we combine this trio with another trio on the right side, then with a root, then we have a perfect tree. This is a balanced binary tree, which means that and from the looks of it, it's somewhere close to this, in the sense that we want to fill up as many spots as possible. So, I think that this might be a decent call to make, in the sense that perhaps we could use this pattern. What we'll do is that we'll form these trios on the left and the right side of the root, because we know where the root is. It's always going to be in the middle. And then for the most recent middle that we see, so this will always be mod 3, where the index mod 3 is equal to 1. That is our most recent middle on left or right. But in the case that we don't have one of those, then we need to consider maybe a left or right. Well, we'll need to consider the left if we don't have one of those. So that's something that we'll have to keep in mind. Though, I'm going to quickly check whether or not this actually works against a couple of more test cases. Give me 1 second. You know what? Screw it. We're going for the YOLO. That's probably not the best thing, but we'll say most recent left subtree middle, which is going to be of type tree node question mark. We'll start that as null. We'll go ahead and duplicate this line and call this right subtree middle. We'll need a for each index in this case. And we'll say when index mod 3 and we'll say if I'm actually going to take a weird detour and rather than doing nums for each index, I'm going to just keep a track of this counter. And this is because of the fact that we have this root, and we don't want the root node to interfere, but we do want the root node to reset our counter. So even though this would be 0, 1, 2, and then this would be 0, so this would technically be the left. We want this to be the left, right? So we need to reset it if the number is not equal to our root.val. Else, if it is our root, then we just want to say counter is equal to 0 and move on. But if it's not, we want to do counter plus plus, or equals counter plus 1 mod 3. And we could do plus plus counter mod 3 to be a little bit more concise, but alright. So when counter mod 3 is 0, is 1, is 2, and we need to remember that we also need to remember that our we need to remember that this should change our left and right subtree middles. This solution is probably a lot more complicated than the actual sort of the standard solution, but I think it still works, and I'm gonna go for it still because, well, I think it still works. And then we can talk about sort of maybe a better approach later. So I'm gonna need a counter or a boolean here, or actually, when our number is less than num size divided by 2, num is greater than the middle, and when it's equal, we can just say counter is equal to 0. We can get rid of this. We can get rid of that part. We do want this part, though it is looking a little bit ugly. And of course, the code repeat here is a little bit unsightly. We can get to that later. And we can say counter is equal to counter plus 1, or plus plus counter mod 3. I actually do wonder if these when statements will interact with this outside? I believe it should. So let's go ahead. If it's a 0, then it should be on the left, right? So left subtree middle dot left. Let's say question mark dot left is equal to tree node of num. Tree middle dot right is equal to tree node num. And we can just actually say val new node. We can just create this in here if we want. Actually, it's fine because then we'd create an additional node here, though I guess it's not the end of the world to create an additional node that immediately gets garbage collected for the root. The problem is that if this is a null, we still want to create the tree node and we want to keep a reference to it. This is starting to get a little bit unwieldy, but let's create a left orphan node. And a right orphan node. And it dot left is equal to tree node num. Run. So if this is null, then we run left orphan node is tree node num. The idea is that if left subtree middle is null, if it's null, then we need to add our tree node. Then we need to add it. So we need to say left subtree middle is equal to tree node num, and then left subtree middle dot left is equal to left orphan node. Otherwise, if we've seen, then we want to say val new node is equal to tree node num. New node dot left is equal to left subtree middle. So the previous middle is now the new left of middle. And then we want our left subtree middle is equal to our new node. And this should never be orphaned, so we don't need to worry about that. It's only our left node that has the potential to be an issue. The problem is that this solution is still really unwieldy. If in the case that we have 3 nodes, we don't set a left subtree middle, because that's the first node on the left of, that's the first node, so it should be on the left. But then we can consider that if at the end when we're connecting it, if there is a left subtree or not, and if there isn't, then we connect to the node. I think we have effectively the same situation here with the right subtree middle. Where we want our right orphan node. Yes. We still want it to stay in left, right, middle order. If right subtree middle is null, then right subtree middle is equal to tree node num. And then right subtree middle dot left is equal to right orphan node. Otherwise, we create a new node. Set our new node to our right subtree middle dot left. Oh, do we actually want to flip it around? No, because anything that comes after will still be higher, so it will be on the left, yes. Right subtree middle is equal to new node. Oops. And then right subtree middle question mark dot right tree node num. Now, at the end, we need to say our root dot left is equal to either left subtree middle, and if left subtree middle is null, then we want to try running for our left orphan node. Right subtree middle, so same thing, right orphan node. So this is a little bit complicated logic, and this is way more lines of code than I would have expected for LeetCode Easy, and I'm anticipating that this is an overkill solution, or maybe even an incorrect solution. But we'll run it, we'll see if we run into any issues, and then we'll see where we go from there. Smart cast to tree node is impossible because left subtree middle is a local variable that is captured by an encasing. We'll do it the old-fashioned way. Left subtree middle dot left is equal to tree node num. Imagine that this may fix the issue, but I'm not entirely too sure myself. Because right subtree middle is it's there. Looks like we have a typo somewhere. Line 98. There it is. Let's see. this is line 74 U. Right subtree middle. Did I make that mistake anywhere else? Don't think so, but left subtree middle on line 49 is still bugging out. Smart cast the tree node is impossible. This is a local variable. Because left subtree middle is a local variable that is captured by changing enclosure. I'm not sure what that actually means. Right subtree middle. That is equal to tree node. No. Are you complaining that this is not line 74? Yeah, you are complaining there. Why are you complaining there? I mean, it's fine if you want to complain there, but that's an odd one. Line 80. This, it is not. It is not happy about it. It's null, then we set it. It's at the left. Honestly, I'm not too sure about this error. I'm probably gonna have to search it up because this is a little bit awkward. Let's see. Okay, that was a strange issue. So apparently there's some, looking at Stack Overflow, looks like there's something to do with for each that just makes it not quite work. However, replacing the top line with just a for each in a similar way that it works in Java seems to make it work, so yeah. Anyways, running the code, it seems like it ran fine for this test case. Let's run it through the other test cases. I just really want to see what it does and see if something breaks. It seems like it's not breaking. So let's toss it through the submissions and see if something else breaks. Okay, something else did break. Awesome. 0, 1, 2, 3, 4, 5, 6, 7. Oh, interesting. For some reason, my final answer just completely gets rid of the 0. Interesting. What's going on there? Zero goes on the left. Then 1 gets there. I really have to see what's going on. We'll say print line attaching left subtree middle left orphan node dot val 2. New node, left subtree middle. This should actually be here. So this is nearly correct. It's just that for some reason that 0 just up and disappeared. Yeah, let's add safe calls to each of these. Attaching 0 to 1. Interesting. New node dot left is subtree middle. Subtree middle. Left subtree middle becomes not null at that point, right? Why doesn't this fire? The middle is 4, so it should be left, right, or left, middle, right, left. Does that actually work? Left, middle, right. Oh, I see. Then the 3 actually overrides. The 3 actually overrides the 0 in that case. So we want to make sure here also. But where do we toss that 3? That's a good question. Where do we toss that 3 so that it makes sense? Maybe there's a better way of constructing this. Now I'm thinking of just a bunch of alternate solutions. This one is a doozy. I probably shouldn't have started this so late. Damn. Okay, I see the problem. But let's see. If I do this here, say that I toss a 3 here. Would that be balanced? No. We'd want the 2 there, because ideally in this case a balanced tree would be 2, 3, 1, 0, like that. Actually, there's no way to balance it evenly like that. What is the tree that they want us to get? They want 4, 2, 6, 1, 3, 5, 7, 0. Okay. Okay. That's difficult then with my current setup, because technically when we attach 3 in that case, because 1 would be the middle, 2 would be there. We could say that if a middle exists, then we want to move it such that our right side, but there's no guarantee that a right side exists. I'm gonna spend a lot more time thinking about it. These were like 10-minute think sessions, but I need a lot more time to think about it. This solution is already way too big, especially for LeetCode Easy. It shouldn't be like this. There must be, or at least there should be, an elegant solution. I'm gonna go find it. So I'll be back much later. Okay, this took way longer than I expected. Where should I even start? So, took a double look at sort of the strategies I could use for this, and one thing that popped into my head was the idea of trios, like before. But what I realized is that we can sort of split the work into each section of the array and then slowly try to build up from there. So that's basically what I'm doing with this approach. It's a little bit of a mess with all the print statements. It took an embarrassingly long amount of time to actually get this recursion to work, but it's at the point now where it actually does work, and I'm fairly happy about it. So basically what it does is that if there is a single, so if there's no difference between the right and left, it returns a single node at the array that's, or at the value it's at. If there's 2, it links them up, left attached to right. Otherwise, it creates a trio, or if there's more than 2 in this case, then it'll recurse. This is just a very, very small optimization, I think. I'm gonna try out the test cases just to make sure that nothing actually broke. And if this works, then I'm gonna go ahead and submit. And honestly, hope for the best. This, I'm gonna be honest, took a lot longer than I expected, and I'm fairly tired. Don't do LeetCode at 11 p.m. But it seems to be working so far. Let's see if it continues to work for the submissions. Now, this is a divide and conquer type of solution. If we have a perfect tree, then we'll have a situation where we sort of have to build up the solution from there. Oh gosh, recurrences. I'm not great at recurrences. But ultimately this is a solution that I'll have to come back to, like for sure 100% on this one, because man, this one was a mess, and I'm not even sure if it works. Okay, so it does seem to work. The runtime and memory is acceptable. It's about average from what it seems, so I guess I was in the right direction. But oh man, this took way too long, and I'm not even sure how to calculate the runtime. Maybe I'm just tired, but this recurrence relation, I'm willing to say it's still O of n log n, just due to the fact that we are having the array each time, but then we need to build it up. Uh, and in the worst case, if we have a bunch of singles, then we would have to run through n operations. That's like my back of napkin, definitely not accurate, but sort of BS justification for that for now. But this, all I can say is that divide and conquer was in my mind to solve this problem due to the fact that really the problems that we're solving underneath were binary search trees, and perhaps this is also the case for a lot of other tree problems, is that the problems don't really overlap with each other, so we don't need the additional context necessarily from them. Therefore, we can solve each part individually on its own and then return the result. And that's sort of the bread and butter of a divide and conquer approach, because of the fact that these problems are not overlapping, so we don't need the additional context from pre-processing before in a way that we would need it for like a dynamic programming approach. But in any case, I'm going to call it here and probably head off to bed after this. But I hope you learned something, and I'll see you for the next problem.